All right. In our second example here, we're going to again look at reducible second order differential equations. And in this case, or second case, it's going to be the case where the independent variable x is missing. I guess I write that there. X is missing, which means we have a function of the form f of y prime, and y double prime is equal to zero, the homogeneous case. And so with this substitution, again, like we did before, p equals y prime, dy dx. We're going to utilize relationships among the derivatives. So y double prime is equal to dp dx. That's this relationship there. Um, and then we are subbing in dp dy dp dx with this relationship here. And so we get p, which is the dp or dy dx here, times dp dy, which is that. Okay, so that allows us to transform this second order differential equation with the independent variable missing into this first order differential equation f of y, p, and p times dy dx. Okay, all right, so that may feel a little bit out of the blue, if you will, or a little bit confusing with the notation. So let's look at an example to kind of make some sense of this idea a little bit to be a little bit clear here. So on our example, I guess I'll call it example two, since it's the second version or second order. I don't know what to call it. All right, so y double prime is equal to right, that is y prime squared. Okay. And so if this was our differential equation, you'll notice that I have y double prime, a y prime, and a y, but I do not have an x. So we can go ahead and make this substitution. So we'll let y prime be p, and we'll let y double prime be p dx, and y stays the same. So if we make that substitution, then this differential equation becomes y dp dy times p. That's this part right here, equals, and then the y prime is p, so it's going to become p squared. Okay. And so this form of this differential equation is really nice because it allows us then to quickly write this as a separable differential equation. And so we can just simply integrate both sides. So I'm going to divide both sides by p, and then multiply both sides by dy, and divide both sides by y. And so moving everything over to one side that's a more efficient way of saying that. We're going to get that dp over, it's like p is going to equal, looks like dy over y. So integrating both of those, you're going to get the natural log of p is equal to the natural log of y plus a constant. And then integrating or using exponentiating both sides, looks like this becomes p is equal to, looks like we'll call it maybe c. Well, call it c1, call it c y. Okay. And then remembering, of course, that p was dx dy. We can dy dx, sorry. We can write this in the form where we flip this. So y p was dx dy. Yeah, that looks like a good idea. So let's do that. So this is dy dx is equal to cy. Um, so looks like I can get this as a function of x in terms of y. So switching x and y as variables, that might be an appropriate move here. So I'm going to reciprocate both sides, and I'm going to get dx is dy is equal to, looks like 1 over cy. And I think it'll be clear in a second if you're wondering why I'm doing this. So then if I move this over, I get dx is equal to dy over cy. This c is just another constant, so I can call that something else, another c, dy over y. This c and this c are not the same. They're reciprocals of each other, but it's an arbitrary constant, so that's okay. Integrating this and integrating that, I'm going to get x as a function of y is equal to, looks like on C, natural log of y. And I'm going to have then, of course, another constant. Let's call that one C1. Okay. And then if I want to, let's say, solve for y and reverse these, let's see, you could subtract that C1 over, call it a new C, and then exponentiate both sides. Yeah, so x minus C1 equals C y, or natural log of y, divided by C, and then exponentiate one more time to get e to the x minus C1 over C is equal to y. Um, just a little bit of cleanup here on the IL2, if you will. Uh, e to the x over C minus C1 over C is going to equal e to the x. I'll call that a new constant. I'm going to go with b. So 1 over c is b, and then this is e to the negative c1 over c. And this I'll call a new constant a, or a0, I like that better, equals y. So finally, then our solution is y equals a0 e to the bx. So you get two constants of integration, which is what you should expect from a second order differential equation. And so there is our solution with the substitution of letting y prime equal p and recognizing through uh, derivations of the representations or dependency on the derivatives here to let p dy dx. Sorry, p dy d. Oh my gosh, it's p dy dx equaling our second derivative. Okay, all right, I hope that was helpful, and I will see you in our next